Okay, hello everyone. Let us continue the third part of today's class. Okay, in the second part, we have said that for a circled set, what does this mean? Okay, if for all x in C and scalars S, if the absolute value of S is equal to 1, then S times X is in C. Okay, so Sx is equal to e to the power of j theta times X is also in C. And in the senior high school math, okay, we know that when we times e to the power of j theta to X, okay, on the complex number plane, okay, it means that we rotate X by theta, okay, by an angle theta. And now theta is belongs to 0 to 2 pi. Okay, so okay, it is equal to rotate X from 0 to 2 pi. Okay, so like this. Okay. Okay, so we will have a circle. Okay, circle through X. Okay, like this red circle, centered on the origin. Okay, in the one-dimensional complex subspace generated by X. Okay, here. Okay, so like this. Okay, and then let us continue. Okay, 3 balanced. If for all x is in C and scalars S, okay, if the absolute value of S is smaller than or equal to 1, then S times X is in C. Okay, if K is equal to R, okay, this means that K is the set of all real numbers. This means that if X in C, then C contains the line segment between X and minus X. Okay, let me draw a graph for you. Okay, let me clear these things. Oh, okay, so first let me select these things. Okay. Okay. So now, okay, K is equal to R. So let me draw an arrow. Okay, it denotes the real number line. Okay, excuse me. Okay, and here is the origin, 0, and here is X. Okay, the point X. Okay, then if S, the absolute value of S is smaller than or equal to 1, okay, then okay, Sx is in C. Okay, it means this. Okay, and we know that if the absolute value of S is smaller than or equal to 1, okay, it implies that minus 1 is smaller than or equal to S and is smaller than or equal to 1. Okay, then what does S times X mean? Okay, it means that the set, okay, the set, okay, Y belongs to the R, set R, which contains all real numbers. Okay, and y, okay, minus x is smaller than y, and y or equal to y, and y is smaller than or equal to x. Okay, this set also belongs to C. Okay, like this. So we can know that it is, okay, let us label the point minus x here. Okay, and let us draw the line of this set. Okay, it should be this set. Okay, so this set is in C. Okay. Okay, so it is the line segment between x and minus x. Okay, and for k is equal to C, that is, k is the set contains all complex numbers. It means that for any x in C, C contains the disk with x on its boundary, centered on the origin in the one-dimensional complex subspace generated by x. Okay. Okay, let us see what does this mean. Okay, let us delete this. Okay. Okay, good. Okay, so now let us consider the complex number plane. Okay, like this. Okay, this is the real part, and this is the imaginary part. Okay, and this is the origin. Okay, so let us x here is the point x. Okay, so if the absolute value oh, sorry, if the absolute value s is equal to smaller than or equal to 1, okay, it means that, okay, s can be written as the form r times e to the power of j theta. Okay, like this. Okay, where r is between 0 greater than or equal to 0, and r is smaller than or equal to 1. Okay, and theta is greater than or equal to 0, and theta is smaller than or equal to 2 pi. Okay, like this. Okay, so then s times x is in C. Okay, so let me write xs is in C. Okay. Okay, so what does this mean? Okay, it means that consider the set. Okay, z. Okay, z is any complex number. Okay. Okay, and Sx is in C, so x r e j theta is in C. Okay, so it contains all the x times r times e to the power of j theta, where, okay, 0 is smaller than r, and r is smaller than or equal to 1. Oh, sorry, 0 is smaller than or equal to r, and r is smaller than or equal to 1. And, okay, 0 is smaller than, oh, sorry, not theta. Okay. Okay, and 0 is smaller than or equal to theta, and theta is smaller than or equal to 2 pi. Okay. Okay, so this set is in C. Okay, in the set C. Okay, so what does this mean? Okay, when first we consider R x times R, where R is greater than or equal to 0 and R is smaller than or equal to 1. Okay, it means that we point times a scalar on x. Okay, and the distance between the origin and x will become x times R. Okay, so between this, okay, so we have this. Okay, we are on this line segment. And 0 is smaller than or equal to theta. Theta is smaller than or equal to 2 pi. Okay, it is equivalent to rotate this line segment. Okay, centered on the origin. Okay, so we will have a trajectory like this. Okay, with the circled, okay, be filled. Okay, like this. Okay, so okay, C contains the disk with X on its boundary. Okay, this is a disk, and centered on the origin. Okay, it's centered on the origin in the one-dimensional complex subspace generated by X. Okay, generated by X is the real part and the imaginary part. So it is an one-dimensional complex subspace generated by X. Okay, equivalently, a balanced set is a circled cone. Okay, what is a circled cone? Okay, let us see the point 4. A cone when the underlying field is ordered. Okay, what does this mean? Field is ordered. We will see the meaning of this field is ordered later. If for all x is in C and 0 is smaller than or equal to t, t times x is in C. Okay, what does this mean? Okay, let me draw a graph for you again. Okay. Okay, so for example, okay, for example, k is equal to r now. Okay, that is k is the is the set that contains all real numbers. Okay, so let us draw the real numbers a real numbers line, and this is the origin. Okay, and for all x in C, okay, for example, if it's the point x and 0 is smaller than or equal to C, then tx is in C. Okay, so tx is in C. Okay, it means that okay, y is in the set of real numbers R, and given that okay, y is equal to tx and 0 is smaller than or equal to t. Okay, this set. Okay, so what does this mean? Okay, it means that for all the number x times t, where t is greater than or equal to 0, tx is in C. Okay, it is in C. That is y is in C. So the graph of this set is equal to the positive, all the positive real numbers and the union with the origin. Okay, like this. Okay, so next, okay, let us see, okay, another example. Okay, so if k is equal to c, okay, that is the set of all complex numbers. Okay, what will happen? Okay, let us draw the figure again. Okay, this is the real part. It is the imaginary part. And again, x is a complex number. Okay, here. Okay, so now, okay, for all x belong to C and 0 is smaller than or equal to t, tx is in C. Okay, so we can see that tx is in C. Okay, what does this mean? Okay, so now tx is equal to z. Okay, is in the complex number set. Okay, and given that z is equal to tx, okay, and 0 is smaller than or equal to t. Okay, so it is equivalent to that z is equal to t times x. Okay, and t is greater than or equal to 0. Okay, what does this mean? Okay, it means that the distance between the origin and the x, okay, it is equal to excuse me. The distance between the origin and x is scaled by a positive or 0 constant t. Okay, so the this set, okay, this set is is in C. Alright, so what does this set mean? Okay, this set is this line. Okay, okay, line segment. So, okay. Okay, so this is a cone. Okay, and then what is a circled cone? Okay, let us see. Circled cone. Okay. Okay, if k is equal to c, okay, it means that for any x in C, C contains the circle through x. Okay, C contains the circle through x. Okay, so we can see that. So now what is the circled cone? Okay, if we want to make this cone to be circled, okay, then we need to rotate this line segment with respect to the origin. Okay, so what is the result? Okay, the result is all the complex number plane. Okay, so does the total complex number plane is a balanced set? Okay, let us see. Okay, for k is equal to c, it means that for any x in C, okay, C contains the disk with x on its boundary. Okay, what does this mean? Okay, x is here. Okay, and the set C contains the disk with x on its boundary. Okay, here. Okay, so it is correct because the total complex numbers plane contains this disk. Okay, so okay, So a balanced set is a circled cone when k is equal to c. Okay. Okay, let us clear this example, clear this graph. Okay. Okay, so next let us see the fifth point. Okay, the point 5. Okay, point 5, absorbent or absorbing if for every x, small x is in capital X, there exists R which is greater than 0, such that X is in Tc for all T is in K, satisfying the absolute value of T is greater than R. Okay, the set C can be scaled out by any large value to absorb every point in the space. Okay, what does this mean? Okay, this is a more complex case. Okay, let us see. Okay, so now we can see that a set is absorbent or absorbing if for every small x in capital X. Okay, let us review what is capital X. Okay, capital X is a vector space over K. Okay, so now that let us assume that simplest case. Okay, so now if we that K is equal to R, equal to the set of real numbers, and X is equal to K, is equal to R. So X is also the set of all real numbers. Okay, so again we can plot the line of the real number and the origin and the point X. Okay, like this. So for every X is in X. Okay, so it means that for every X in the set R, there exists a small r which is greater than 0, such that X is in T times C. Okay, for all T is in K, satisfying the absolute value of T is greater than R. Okay, so we can see that for every, that is for all X is in, is in capital X, that is in the set of real numbers, there exists, R is greater than 0. Then such that, X is in Tc, X is in Tc, for all T is in K. Now K is the real, the set R, real number, set of real numbers, satisfying, satisfying, the absolute value of T is greater than R. What does this mean? For example, now with that X is equal to 1. It is a real number. And there exists R is greater than 0. So let are. Okay, it is 25 minutes. See you next time. Goodbye.